contains two types of the valencies. That two valencies we have as called primary and the secondary. Primary is ionic and the secondary is non-ionic, means it is not ionizable. Okay, the primary ionizable valency satisfied by only negative ions, whereas secondary non-ionizable satisfied by neutral molecules or the negative. Possibilities there, the approaching ligand can be molecular in nature or can be containing a negative ion over it. Primary valency oxidation state, right, that corresponds to the oxidation state of the central metal atom or to the central metal atom. Secondary valencies corresponds to, we can say, the coordinate bond, what coordinate bond present between metal atom and the ligand. Okay, so I have explained over here by giving example about all the above what I have written in a sentence. I have explained here. Then next I showed that primary valency is variable, whereas secondary is fixed. Variable, why? Because the valency of central metal atom is variable. Iron can exist in +2 state as well as in +3 state. You could have like yesterday, right? You can just imagine that you now that is the option for you. You can go for that example. Fe3, we have two compounds, Fe3 plus के साथ and Fe2 plus के साथ. So the compound can go in a ferricyanide as well as in a ferrocyanide. So why is that so? Because central metal has variable valency. Second, direction and non-direction based, you can see all coordinate bond going towards to metal atoms. So secondary is directional, whereas primary depends on only values, oxidation state basically. So it is non-directional. That's all about the Werner's theory. Okay, any doubt? Do you have any doubt?
No, ma'am.
No. Okay. So let's move on to, so now you are clear with how to find the coordination number. You are clear about the Werner's theory. All these concepts are clear to you, isn't it? Can we go for the classification of the ligands now? So we can start then oxidation state calculation and the IUPAC nomenclature, which is the main part of this chapter. Can we go for now? Let us start the next topic, ligands. So what are ligands? You can see the central metal atom is surrounded by molecules. Okay, those molecules are called ligands. So they can be present in a molecular form, they can be present in a negative ion form, they can be present in a positive ion form. So there are different types of the ligands. If the definition asked for the ligands, we say the ions are molecules. Basically, what are ligands? Ions. It can be in a form of ions, it can be in a form of molecules. Okay, so ion are molecules. What do? They donate a pair of electron to central metal atom. So we write ions are molecules which can donate one or more pair, one or more lone pairs, right? So pairs of electron, where do they give? Can you help me? To the central metal, right? Ion you can write or you can tell atom, no worry. So central metal ion, why do we focus, why do we specify in an ionic form? Because it exists its oxidation state, right? There +2 or +3 or +1, whatever the oxidation state it carries. So ligands, what are the ligands? Ligands are molecules which can donate a pair of electron to central metal ion. That's all. Okay, now if I'm talking about the types, it's a huge family actually. So basically we have monodentate. By as this classification I would be doing, or types I would be doing based on their ligating behavior, right? How many electrons do they ligate? Are you understanding ligating nature? Ligating means donate. How many electrons are getting donated by the ligands? So ligating nature. So it a ligand donates a pair, one pair of electrons. So we call it as a monodentate. If a ligand donates two pair, So it's a simple concept. If a ligand donates two pairs, suppose A is a ligand which can donate one pair. So I would put this A in a monodentate category. Why? Because this is able to ligate with a lone pair of electron, isn't it? So I will say this is a monodentate. If suppose we have B, which is able to ligate with its two pair of electron, so I would put this in a bidentate category. Why? Because it can ligate with its two pair of electrons. Are you understanding, Hridaya? So
Yes, ma'am.
types or classification, how do we do? Based on its ligating nature. Ligating is nothing, it's like a donation, how many electrons we can donate, or we can see by donation by from the molecule or from ions. So based on that we do the classification. Clear? So let's have some now names over here. So what are the types we have? Let's go monodentate. The first goes monodentate. Monodentate ligands. So the ligands which can donate. So here I would write only the keyword. Okay, can donate only one pair of electrons to the central metal ion. We call it as a monodentate. Clear? So here we go with the examples. What are the examples do we have? We can have like many are there. Here, let me classify it into positive and neutral. So let's begin from the neutral, then positive and negative. Okay, the category goes under this. So you can see easily like they will not be carrying charges. So those are like placed in neutral category, and those who are carrying positive ion placed in positive category. Those who are carrying negative charges placed in this category. So here we go. Hridaya, Hridaya, can you
Yes,
hear me?
ma'am. Yes,
Yeah,
ma'am.
I'll be writing the names in bracket. Little enlarge this slide because I need to have some more space over here. So I would be writing the names beside them. So that indicates the IUPAC name. Okay, so the same name will be used when we are doing the IUPAC nomenclature. So we
Yes,
are not going to learn in a separate. Here, whatever we have learned about the ligands, it is continued in the IUPAC. Clear? So let's learn about the neutral ligands. Ammonia. Does ammonia carry any charge? No, it carries a pair of electrons. So this is called by the name amine. What do you call this name in IUPAC nomenclature? Amine. Aqua, water, like aquafina bottle, right? So IUPAC called water as the aqua. AQUA. Understood? So this is also a neutral ligand. Clear? See, you can see there are two pair of electrons, but what happens? It just ligate with only one pair. Are you clear?
yes, ma'am.
Carbonyl. The next is the carbonyl. So these neutral you need to pay attention. Why? Because it helps you to calculate the oxidation state as well. The next step we are going to learn the oxidation state. So whenever it is asked what would be the oxidation state of ammonia, so you will say it is zero because it belongs to the family neutral ligand family. Does not have any charge over it. So that is carrying zero. Clear?
Yes,
Remember it. Carbonyl. The next is carbonyl, right? Next, after this, NO, nitrosyl. Okay. So these are the molecule which we have considered as the neutral ligand. Then the positive one, we do not have much in the positive. We have very less positive ligands like nitronium and nitrosonium. So the first go over here as the NO2 plus. What do you call this as the nitronium? Nitronium. So when it comes to the molecular formula seeing the plus charge, what you will call the name as nitronium. Two removed and just NO plus left, so called it as the nitrosonium. What do you call this as? Nitrosonium. It is clear to you? Clear, right? Okay, negative. Let us complete the negative. Negative, we have large family. So here we go, cyanido. So it is called as in by the IUPAC nomenclature as the cyanido. right? Second chloride ion we have, which is called as chlorido. Okay, like this family will be there Br minus, so you will call it as a bromido. Suffix will be added in all the names you could see, right? Then florido. It is clear, right? Then SCN minus. Basically, it is thiocyanate, right? Sulfur ke liye we use the word thio, and CN is cyano. So cyanato, thiocyanate. It is clear? Please confirm it is clear.
Yes, ma'am.
CH3CO minus, acetato. Why do we say these all ligating with only one pair of electrons? So they are all categorized under that monodentate, and you can see all have carried one negative ion as well. Even two negative ions molecule also will be, because they will be ligating with one molecule. So here we go with the hydroxo. It is called as hydroxo. Okay, so mono has a big family, monodentate. Okay, then oxide ke liye we use the word oxo. Okay, then NO2 1 minus ke liye we use word nitro. Okay, and then after we have, suppose we is NO3, right? NO3 is nitrito. And the last, sulfato. And carbonate also, let us write. Sometimes they ask carbonate or sulfato, carbonato. These are the suffix, nato kind names. Okay. Here, let me introduce this compound. This compound is actually having dual nature. Sometimes it ligate with the nitrogen as well as with the oxygen. So when the case with the oxygen is specified, so we write in this order. ONO. Then what do you call the name? Like here you can specify it. Now oxygen is ligating. So you can say the name of this as the nitrito. So by the name, we will be like very much confident that the ligating atom is oxygen, not nitrogen. Are you clear, Hridaya? By these all names and the symbols, any doubt?
No, ma'am.
No, right? Okay. So we will be using these table again when we are doing IUPAC nomenclature. Okay. Let us go for the bidentate or called as didentate. So bidentate suits very well. So we will be writing bidentate. Now you can define what do you mean by bidentate ligands? What are bidentate ligands? Tell me. Can donate
Two.
two
Okay.
lone pairs. Exactly. Can donate two lone pairs. To whom it will donate?
The
To the
central
central
metal.
metal atom. Exactly. To the central metal ion or metal atom. Okay. This is about the bidentate. So let me give you some examples that this does not carry much in your syllabus. It has huge family, but have given very less examples over here. So here we go with the example. The first is oxalato. Okay. Oxalato ion. So here we call it as the oxalate ion by the name. So you can write even the oxalate ion, Te suffix. Okay. Now look at over here the symbol. Okay. So COO1 minus, single bond, OO1 minus. You know oxalic acid, COH, single bond COH. I removed hydrogen and kept the hydrogen in place of hydrogen, one negative ion over oxygen. So now oxygen pair will be ligating. So the arrow you can see, right, coordinate bond. This coordinate bond indicating oxygen is ligating, right? So how many ligating atoms do you have? One and two, correct? So what do you call this as? Bidentate ligand. Are you clear?
Yes, ma'am.
So we can write in the molecular formula के form में C2O4 2 minus together. Okay, 2 carbon, 4 oxygen, and how many ions are present? Total 2 negative ions. Second example, which is very, very important, both are common. Let me introduce you with the abbreviation form. What do you name this as? OX, OX. Okay, as well. So now ethane, next compound, here we go, ethane 1 comma 2 diamine. Okay, so this compound, it's very simple. You know ethane, right? So let's draw the carbon single bond and the first and second number. So we have the amine group as well attached. We know amines are trivalent, means nitrogen is trivalent. So we will be having 3 bonds. Already one bond is attached with the carbon, 2 more stick that will hold hydrogen. So we are clear with the structure. Now let's see about the carbon stick. Carbon is tetravalent, so 2 hydrogen needed to complete its valency. So you could see, right, every atom has their valency stick around it. So we can say carbon 1 and 2 holds 4 stick around it, nitrogen holds 3 stick around it. So we call it as a ethane 1,2 diamine. What is the abbreviation form of this compound? En. Are you clear?
Yes, ma'am.
Okay, let's move on to polydentate ligands. Polydentate with the ligands which are ligating with the more, right? More than 3, 4, 5, like the category goes over there. So we can all can kept in the one that can be called as a polydentate. So third category goes as polydentate. Polydentate ligands may we can say that ligands which can donate many lone pairs, right? Ligands which can donate many lone pairs. So we can call it as a polydentate ligands. Correct. So here to whom they donate, it is central metal ion, right? So I'm not writing that. You can copy from the previous definition. Even you can frame it by yourself. Example, here we go. The most important example is E, D, T, and A. Let me brief about this. What is E for? Ethylene. What is D for? Diamine. And what is T for? Tetra. And A for acetate. Are you clear? So I'll explain. Ethylene. So carbon, we know basically double bond, but over here, look at over here, the structure is very huge. So first I will be drawing the ethylene. So carbon, let me write the 2 carbon, but here what happens, we say the carbon double bond carbon goes in the single bond because okay, let not to put hydrogen, otherwise I cannot explain you in a basic structure. Yeah, so we know around the carbon there will be 4 stick, right? So here we go with the nitrogen terminal sites. Why? Because we have diamine. So as usual, those that is structure which you have studied, the same would be taken over here. But we have how many acetato? Acetato means 3CH3COO1 minus. How many moles you have? 4. So these also are getting attached. So how will you attach? Look at over here. Stick you need to remember. These are the arrangement. Then carbon and carbon. Are you clear? Carbon and carbon. Clear? So what I'm going to do is I'm going to show over here why did put double bond over here. The reason behind it, it is ethylene. I accept the ethene is called the ethylene, but here carbon like further attached to the nitrogen which holds like we can say acetated too, right? So this has, we can say, one nitrogen, so it must carry, we know, because the carbon which holds the 2 hydrogen, right, we can call it 2 carbons with 2 hydrogen, we call it as a ethylene. It is like we can say it depends on the nature of the carbon further with whom it is attached. So nitrogen it is attached, so not possible holding double bond in between, right? It is clear, right? 4 bond already satisfied, no more bond can exist. Are you clear, Hridaya? Now
Yes.
acetato, see acetato ka structure, how it will be written. Already one bond is done, correct? we need next carbon with the double bond oxygen. I'm talking about this double bond oxygen, a single bond oxygen. Are you clear? Let's do justice with this carbon also. How many hydrogen does it require? Two hydrogen, two more hydrogen, right? Are you done? So it means the acetato, we know the formula is CH3CON minus, but since it is attached with the nitrogen, so it is holding CH2CO1 minus. One hydrogen has gone in making single bond between nitrogen and carbon. Are you clear? Similarly here. So all four sides, we do that arrangement. If you anywhere you are not able to understand, ask the question, Hridaya.
Yes, ma'am.
Same structure continued four times because tetra it is. Clear, Hridaya?
Yes, ma'am.
So every now we can say the lone pair side, we can have nitrogen lone pair present, oxygen already we have the lone pair which is ligating. So coordination bond you can represent. Now representing the coordination bond. Now different all the sides you could see this is ligating. Okay. So here we go with the two sides, three sides, the pair of electrons with the oxygen. We know every oxygen will have, so here we go with the two, right, which will be ligating. From here it will be ligating. From here it will be ligating. So you can see from six sides, this molecule is ligating. So we can call this as the polydentate, EDTA, ethylene diamine tetraacetate. So structure is not very important, Hridaya, for you, but example EDTA, remembering it's very important. Okay. Did you understand the structure completely? Why did we call it as a ethylene? Because two carbon with the four hydrogen, or and sorry, two carbon, each carbon with the two hydrogen. Diamine, we have two nitrogen. Every nitrogen with the pair of electron. Tetraacetate, we have acetate ion four times. So that is why it is tetraacetate. Is this clear?
Yes, ma'am.
Which type of ligand it will be, we can call it, category can go with the hexadentate, means it is ligating with the six ligating atoms. Are you clear? I have shown you the six sides. Let me highlight. So now you can see each side three, and like this we can have six. So this is all about the basic classification of the ligands. Here we go with the one special category, but this also comes under the, I would say the mono only, but it has a special nature. So let me introduce this type to you. It is ambidentate. What do you call this ligand name as? Ambidentate ligand. What do you mean by ambidentate ligand? It means it would have, like, MB means dual, right? Behavior, right? Nature, or it is having characteristics where we can have possibility maximum, both the both possibilities, two possibilities, right? So here if we are talking about ligands, and when we have classified based on ligating atoms, so definitely here I am talking about the ligating atom, which available two types, right? But one at a time, right? Not both at a time. One at a time would be ligating. So such ligands we call it as a ambidentate. Okay. So let me write this. And what are ambidentate ligands? Containing, these type of ligands will be containing more than one donor atoms, but which can ligate, ligating in the sense link, correct? Donating and getting linked through only one donor atom. Are you clear? Such type of ligands we can call as a ambidentate ligand. So let's see the example, then it will be more clear to you. Cyanide ion. Okay. So in the cyanide, we can say it can ligate through carbon, right? It can ligate through carbon and as well as nitrogen. Both are ligating over here, right? Or you write and you do not write or you, because one at a time it is there, no, or nitrogen atoms. Clear? So look at over here, the cyanide, if I keep like this and I am donating this pair to central metal atom, it means carbon is ligating. Are you clear, Hridaya? It means carbon is ligating a lone pair to central metal atom. This is metal ion. This is ligating atom. The second possibility, I'll keep nitrogen now front, donate a pair. Clear? So what do you call this as the cyanido? When you keep carbon front of metal ion, cyanido. When you keep nitrogen front, this is called isocyanido. Able to understand?
Yes, ma'am.
Good. This is the one example. Let's do the second example. Nitro group. As I said, this will be holding nature now. So it can ligate through nitrogen or oxygen. Okay. So when it ligates to nitrogen, we keep nitrogen front of metal and we call it as a nitro group. But when metal atom ligated for by oxygen, okay, then we call it as a nitrito, where I have written in the chart, correct? Nitrito. A pair is donated from the oxygen side. Are you clear there?
Yes,
Then we
ma'am.
have SCN. What do you call the SCN? Thiocyanate. S is used for, thio is used for sulfur. S. So S ka IUPAC name is thio. Okay. Cyanido. Okay, sorry, cyanato. It's a thiocyanato. Cyanato, I'm saying. Thiocyanato. Okay. So when it is ligating through this, we call it as. So this ligate through sulfur and nitrogen. Okay. So when it will be called as thiocyanato, when sulfur ligate to metal atom. And when it will be called as isothiocyanato, when nitrogen is ligating to metal atom. Right? It is clear now?
Yes, ma'am.
Okay. Now the two things. Chelating and we have denticity. So what do you mean by the denticity? Then the denticity is nothing. Let me clear here itself since we are done about the ligating. So let me clear this small topic. Denticity is nothing. It's number of ligating group. That's all. So if you have oxalate ion, okay, oxalate ion, for example. So what is oxalate ion? C2O4, right? Minus. So one minus over here, one minus over here. It is ligating through the two, right? So what is the denticity of this ligand? Two. Are you clear?
Yes, ma'am.
Huh. So this is the ligating atom, this is the ligating. So since we have two ligating atoms, so we can call it as denticity of this molecule is, or this ion is 2. Clear? It is
Yes.
clear?
Yes,
Okay.
ma'am.
What would be the denticity of EDTA, Hridaya?
Mm,
Yes, Hridaya?
um,
6,
five,
right?
six. Oh,
6, 6. Because it is ligating through 6 molecule, 6
okay.
atoms. Just a minute, Hridaya. I'll be back. 1 minute.
Yes, ma'am.
Yeah, Hridaya. So let us move on to the next topic, chelating. Authenticity is done. The next small topic is chelating complex. So example may I would take EDTA, right? So this complex will be basically polydentate ligands and which will be bonded with the metal ion, right? So they will be ligating through the more chelating in the sense like this structure they will be like a claw like a structure they will make. Okay, so you could see in EDTA we have 6 ligands. So basically, they approach from all the sides to metal atom and they cover it. So basically, what are the chelating complex? A complex in which, where the definition we can say, a complex in which like a crab structure you have seen, no crab how it takes its prey, right? Same way you can feel like all 6 sides it holds all six through all 6 legs it holds, isn't it? So we can say the chelating is compared with that structure. So we can see like the polydentate ligands basically covered the central metal atom looks structure looks like a chelating complex compound. So complex in which we can say polydentate ligands. Even bi also can have option. So keep bi also, bi or poly both. Okay, is bonded. Okay, to a central. Okay, just a minute. With two or more coordinate bond. So when it is bidentate, obviously will be two. And when it is poly, then more. Clear? So what do you call that? Chelating complex. So example may I would say EDTA, ethylene diamine tetraacetate. Okay. Any doubt, Hridaya?
No.
Can we go for the calculation of the coordination number, Hridaya, now? I would give you the complex and then the metal ion. So here we go with the metal ion. This is very important. So nickel is the metal, does not carry any charge because CO is the neutral. So all makes it 0. So does not carry any charge over it. Coordination number, how much it will be, we will have to find out. So in this complex, NiCO whole 4, we are asking. So how do you check? CO is monodentate, so we will have the 4 sides say coordinate bond. So what is the coordination number? 4. Are you clear?
Yes, ma'am.
So we need to check the nature of the ligating. So next is Cu2 plus. In this compound, I am giving you compound name CuNH3 whole 4, right? 2 plus. In this compound, you need to check. So ammonia is monodentate, neutral, right? This is also monodentate, neutral. So how many ammonia you have? Total 4. The number of neutral mono can be that coordination number. So 4. This is also 4. Let us learn in this iron 2 plus ferricyanide FeCN whole 6. This is also monodentate. So how many atoms do you have? 6. So 6 sides it will approach. So what is the coordination number? 6. Did you understand? Fe3 plus. So FeCN whole 6. Correct? This was the 2, 4 minus and this is 3 minus. So here we go. Same. There is no change. 6. Are you understanding the concept?
Yes,
Now
ma'am.
let's do this is quite different. Cobalt. Cobalt C2O4 whole 3 over here sphere. So oxalato is bidentate. It means it ligates with 2 electrons. 2 pair of lone pair of electrons. It means multiplies these with 2 with the 3. So how many bonds will be formed? total 6. Did you understand? So it depends on the nature of ligands. So this all are similar. This is quite different. This is what? Bidentate. So bidentate means two ligating atoms. Are you clear? So that's the reason I multiplied with this 3 and got the 6. So there are 6 coordination bonds. Are you clear?
Yes.
Are you clear, Hridaya?
Yes, ma'am.
Good. Now we can go for the nomenclature part. You have seen the sphere type also can be positive, can be negative, can be neutral. We have learned yesterday, right? Let me introduce one more type of complexes. May I would say the homoleptic complexes and heteroleptic complexes. So what do you mean by homoleptic complexes? When we have one type of ligands present, so we call it as a homoleptic complexes. Okay, homoleptic complex means the complexes in which the central metal ion is surrounded by only one type of ligands. Right, example, if I say NiCO whole 4. Okay, so I would say here in this Ni atom surrounded by 4 CO atom, 4 sides, say. Correct? So we say the what is homoleptic? The complexes in which the central metal ion is surrounded by only one type of ligands. So what do you call that? Are called homo. Homo means same. Homoleptic complexes. Right? So I would draw the structure. Ni in the center, 4 different sides. Say we are seeing the approach by similar ligands. Correct? All are similar. CO, 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 CO. So what you say that? Same ligands, isn't it? All are same ligands. That's the reason I have took the category as homoleptic. Did you understand? Heteroleptic. Now, complexes where we can see different types of ligands. Correct. So let us see the example. PT, central metal atom. Ammonia is one type ligand. Okay, and the chlorine is another type. So inside the entity, this box, whatever comes, like the one will be the central atom, rest all goes the ligand. So this is the central metal ion. As I said, the central metal ion always will be from the D block elements. Okay, so that's the reason one central metal ion and rest all ligands. Are you clear? This is one type and this is another type ligand. So since we have ammonia one type and another type chlorine, so we call it as a, so it can have two possibility. Ammonia can say, go same side, Cl can go or can go different side. Did you understand?
Yes, ma'am.
So this is heteroleptic. Definition you can write by yourself. The complex in which the central metal ion is surrounded by more than one type of ligands. Right? So I would say here central metal ion surrounded by more than one type of ligands. Okay, you can write the definition. So this is called the heteroleptic. Now let us learn the oxidation state. So what are the things we have done so far? We have learned the types of the ligands and the small terms like denticity and the chelating. What do you call that? And then we have come to the coordination number, right? Find out the coordination number for given complexes. We have learned this topic, isn't it? And now let's learn calculation we are going to do for oxidation state. Okay. Oxidation state of the central metal ion, right? Always it will be calculated for central metal ion. So for example, if I have a compound K4FeCN whole 6, how do we calculate? See, the central metal ion we need to identify inside the entity, the metal ion and the ligands will be present. So central metal is the iron. So we need to find the oxidation state of iron. So we need to know first all the oxidation state, rest all. We know potassium is monovalent. So here we go with the 4 atoms into +1. ठीक है, iron, let this be plus x. Okay, and 2 atoms के बीच में the sign will be plus. Cyanide is negative, right? Monodentate -1 into how many atoms? 6. Entity does not carry any charge, so equal to 0. Did you understand how to frame the equation?
Yes, ma'am.
Potassium oxidation state is equal to +1. So I kept over here. Iron oxidation state has to be calculated. So X, Cn oxidation state of Cn is -1. How many atoms we have? 6. So I kept over here. Entity does not carry any charge, so 0. So 4 plus X minus 6, 0. Right? -2, 0. So what is X equal to over here? +2. Did you understand? What is the iron oxidation state? Tell me. It is +2. Are you clear?
Yes, ma'am.
Okay. The next one. CuNH3 whole 4 2 plus. Let's see example this because entity holds 2 plus, means complex sphere is holding 2 plus charge. Then central metal atom copper and rest all ligand, because entity के अंदर what we have, that is the metal and ligands. So copper we have to calculate, so let this be X. How many we have total? 4. But ammonia is a neutral, so 0. And entity equal to +2. So we carry +2 over here. X plus 0 plus 2. What is the oxidation state? +2. So oxidation state of copper +2. Did you understand?
Yes.
Okay. Rest you will calculate. You will try by yourself. You must be needed the chart, isn't it? Can you
Yes.
take the screenshot of this chart in your system or anywhere in a phone? Can you take the pic? So it will be helpful to you. Hridaya?
Yes, ma'am.
So we can work out on this now.
Yes, ma'am.
Have you taken?
Yes, ma'am.
Okay. So now I'm giving you molecule, calculate the oxidation state of that. Okay. So here we go with the one compound NiCO whole 4. You have to see the central metal atom and see the nature of the ligand. Okay. And then calculate. What will be the oxidation state of nickel here?
1.
No, find out and then you tell. What is the nature of cobalt? Sorry, cobalt I'm saying, carbonyl. It's a neutral,
Yes.
neutral monodentate ligand. So since it is neutral, so oxidation state of CO, carbonyl will be 0. That's the reason I told you to take the screenshot. Now, what is the central metal atom? Nickel. Nickel, let this be X plus 4 into 0, right? And entity does not carry any charge, so 0. Did you understand? X is equal to 0. So what is the oxidation state of nickel over here? 0. Do you understand?
Yes, ma'am.
Will you try the next one by yourself?
Yes, ma'am.
NiCl whole 4, 2 minus. You can do it. How did you calculate? Can you help me? You will be right. No worry. Just help me out. How did you calculate nickel as the central atom? And what is the nature of Cl, Hridaya?
Negative.
Negative. Very good. Negative monodentate ligand. So what is the oxidation state of Cl over here, Hridaya?
-1.
Exactly. Very good. So this will be considered X plus, and since oxidation state is -1, entity is carrying -2 charge. So equation will be equal to,
-2.
very good, X minus 4 minus 2, X is equals to -2 plus 4, X brought plus 2. So very nice. Okay, Hridaya, you want break?
Uh,
Do you want break or want to continue?
Ma'am, either is fine.
What is, Hridaya? I'm not able to hear you clearly.
I said it's either is fine.
Okay. So just take a break 2 minutes. I will be giving you examples. After the break, you come back and solve these. Okay.
Yes, ma'am.
Till then, I'll be writing the molecules over here to calculate the oxidation state of that. You have taken the screenshot, all the details with you, right?
Yes, ma'am.
Have some break, few minutes. Okay.
Yes, ma'am.
Come back quickly. Till then, I'll be writing here the names and you calculate the oxidation state. Go and come back quickly.
Yes, ma'am.
Hridaya, are you back?
Yes, ma'am.
Huh?
Yes, ma'am.
So Hridaya, you can start calculating all these.
Yes, ma'am.
Follow the chart, the oxidation state of the ligands. Confusion you have, Hridaya? Understanding the
Mm. I don't know how to do the third one.
yeah, I'll try. I'll help you.
Okay.
What is the cobalt oxidation state here you found?
Is it 6?
Huh?
Is it 6?
Okay, how did you calculate? The compound is Na3CO. Check your answer, F6. Okay, so this is outside and we need to find for this, correct? So sodium is monovalent, we know. So we'll keep this +1 into 3 atoms plus X. This has to be calculated. Fluoride is -1. And how many? 6 are there. Entity equal to 0. Did you do this way?
No, ma'am. I forgot to put the.
No, always this also considered, right? Outside those who are present.
Yes.
Now you calculate and tell the answer.
Will it be 3?
Yeah. +3. The next one, which you are not able to understand, the same exactly over here, K3, right? FeC2O4, correct? C2O4 whole 3. And then inside the entirety. So potassium is +1 into 3, iron let it be X, oxalato -2 into 3 and equal to 0. Are you understanding? So it is +3 plus X -6, 0. Clear?
Yes.
Oxalato is bidentate, C2O4. How many charges it has? -2. So the oxidation state will be -2. Did you understand?
Yes, ma'am.
Do the next one. Are you able to do Hridaya? See, all ligands you need to check the oxidation state. It's 0, -1, and this nitro group is containing -1. Correct? And the entity holds the -1. So equation equal to -1. Now you calculate -1, -1 becomes -3.
Z equal to 2.
PT oxidation state is 2. Very good. Next one you do.
Is it 0?
Correct. Next one.
So 3.
Yeah. So you are able to now calculate oxidation state, Hridaya. If you are
Yes.
confident, then only we'll move on to the IUPAC nomenclature. Still you have confusion in calculation, then we have to practice on it. Because without this, we cannot go for the calculation IUPAC learning. So you once confirm, yeah, you are understood, you don't have any doubt in doing oxidation step, then we'll move on to this. Can we go now IUPAC?
Yes, ma'am.
Sure?
Yes, ma'am.
Very good. Let's move on to the nomenclature now. When we start the nomenclature of the organic compounds, I would like to divide this into, as per its complex nature, complex entity nature. Entity can hold neutral, can charge, right, plus or minus. So cationic complexes, anionic complexes. I would like to divide in that way. So let's begin the nomenclature, which is most important topic of this chapter. Nomenclature in coordination compounds. So IUPAC nomenclature you are going to learn. So it is quite different from the organic compounds because it's an inorganic salt, complex salt, and it follows different IUPAC rules. So we need to know the rules. Okay, IUPAC rules. So let us first begin with the cationic complexes. Okay, so cationic complexes follows a sequence rule, naming rule. What is the naming rule? Here we go with the naming rule. Name of the ligand. Okay, name of the ligands. That will be sometimes alphabetical. This is condition applied when we have more alphabetical order given to them. When they are more, like example, you have seen like this ammonia hai, Br hai, Cl hai, nitro. So like a full crowd of the ligands, right? So how will you name it? So go for alphabetical sequence. Which comes first? Which letter comes first? Written first. That's all. So alphabetical order. So here we do not have the position number like that. All sequence we do not have. The only applicable over here the alphabetical order name will be going. So order will be taken by the list you have given a name na? That list you need to follow. So first go with the name of the ligands. This is the first rule. Then added the name of the central metal ion. Name of central metal ion. Then we go with the oxidation state. Oxidation state. Okay, this will be written in Roman number. Clear? After this, we have the name of simple anion. It is applicable when it is present. Okay, if it is not there, then need not to write. And similarly, anion out right side the complex. So let me tell you one small trick over here. So when we are having a cationic, specifically, either they will be holding the right hand side. Let me tell you, this is the entity, complex entity, where you have the central metal atom and the ligands. So here, left hand side will not be any molecule or atom present. Why? Because it is cationic. So definitely either it will hold the positive over here, or it will hold the anion right hand side. Okay, X can be present here. Did you understand? So that when we ionize, it go in a this form, cationic complex. Did you understand? So whenever it is a cationic complex, the molecule or the simple anion where it will be present, right hand side. Are you clear? So their simple name we have to write. We'll see, we'll learn the molecule example, then we can understand. So either it can be present or the positive charge will be over that. Okay, both the ways are possible. Cationic complexes. Are you understanding? Hridaya, are you able to understand?
Yes, ma'am.
Chalo, we'll start the examples. When we do the example, it will be more clear to you. The example we go over here, cobalt hai, amine group, right? Six numbers. And now you can see I have closed the bracket and I kept the Cl outside. So I meant to say this line, name of the simple anion outside. This is that. Did you understand?
Yes,
See,
ma'am.
here you need not to write 3-chloride or chloride or such name. Simple name. What do you call by Cl as a simple name? Simple name. Tell me. Chloride. Such name will be written. Understood? So rule applicable the atom with the ligands and metal ion present inside the bracket. For them the rules are applicable. Let's begin now. The rule says first ligand, then central metal ion, then oxidation state of the central metal ion, and then name of the molecule or atom or anion which is present outside the box. So how many numbers does it has the ligand? 6. So let us write hexa. Okay. And NH3 is called as amine. Understood? Metal atom, cobalt, oxidation state of cobalt X plus 0, amine is neutral, right? Equation, plus minus over here 3, because minus 1 into 3, equation becomes 0. So when you bring X this side, becomes plus 3. So what is the oxidation state? 3, which is written in a Roman numeral. Got it?
Yes, ma'am.
And no need to write the 3 and 4, because already it is represented by here. Calculation may involved ho chuka hai. So you just write the chloride, simple name of the anion present outside the box. Did you learn? So
Yes,
this
ma'am.
rule is applicable for the cationic complexes. Why did we say this is cationic? There is no sphere holding positive. I know it is not holding, but right hand side may we have molecule. When they go for an ionization, they carry positive over the sphere. That is why we are calling it as a cationic complexes. Are you understanding?
Yes,
Next
ma'am.
example. CO NH3 whole 5 Cl in Cl out Cl2. How do you name? Now this is multi heteroleptic and the many ligands are present. So this letter starts with the amine, right? A, and this will be C, chlorido I meant to say. So which letter comes first? A comes first. That go first. So let's begin. Penta, amine, chlorido, okay, cobalt. Now calculate the oxidation state. This is 0, this is minus 1, right? And plus this is minus 2, equation 0, x. So x is equal to plus 3. Did you understand how to calculate the oxidation state? That's the reason I said if the calculation of oxidation state is having command, then you can do it. So oxidation state written in Roman numeral over here, chlor, chloride, okay? Simple name of this, chloride. It is clear?
Yes, ma'am.
Okay. The next one, Okay. Now, how to write this name? Because this is bidentate, na? And it is having different name actually. So let me tell you, whenever we have this compound where the prefix di word used, we do not use the di tri as for the number substituted. So for them, the word used as a tris, bis, like that. So two if present, bis will be used. If three are present, tris will be used, like this. Okay, so we go with here the compound. Okay, so we call it as a tris. Okay, because three are there. Why did we use tris? I'll tell you. The name of this en is ethane, correct? Comma, 1 2 comma, right? Diamine, bracket, and then after central atom, correct? Cobalt. Oxidation state, let us calculate x 0 plus minus 3 0. So x is equal to plus 3. Understood? So the oxidation state in Roman numeral 3. Got it? Okay. Chloride present. Let us write chloride. Now let me tell you why did we not write the tri over here, because already one name present over here. Okay. The name over here is di. So since already we have taken the di name, right? So if in case if it is 3, no worry. But if in case di 2 is present, then di get repeated. So that's the reason here the name goes for the prefixes specifically for en, prefix for numbers. Okay, so we have applied over here tris, ethane 1 2 diamine. Are you understanding? And why did we write in bracket? Because it is holding di word. So and as a huge name, right? So we wrote it in a bracket. Got it? Tris, ethane 1 2 diamine, cobalt, oxidation state chloride. Are you clear, Hridaya?
Yes.
Okay. Will you do by yourself another example?
Yes, ma'am.
Do this one. Hriday, are you able to do these all?
Um,
No? You are not able to do this?
not exactly.
So you should tell Hriday, I'm waiting for your answer. So look at over here. We have 4 amine, right? And 2 aqua. Correct? Screenshot is there with you, right? So tetraamine, the 4 go for the tetra. It is not En. Na? So if it is En not there, so we can use go for the as usual name, tetraamine. Now here confusion, both the letters starts with the A. So no worry. The second letter.
Um,
Yeah, Hriday, tell the name.
Pentamine carbonate
Super.
cobalt
Very good.
2 chloride.
Uh-huh. Chloride is -1 and carbonate is 2 minus. ठीक है? So -1 -2 becomes -3. And equation के बाहर जाने पे it is +3. How did you calculate? This is x, this is 0, this is holding -2. You know about the carbonate ka charge, CO3 2 minus. It is written in the table also. Plus -1, equation equal to 0. Did you understand?
Yes,
थोड़ा
ma'am.
सा problem in the calculation of oxidation state you have to do, resolve the problem. So I will be sending you the homework for today for writing specifically for doing the oxidation state calculation and the writing the IUPAC name after that. So work out on that today, okay? Whenever you have free time. So
Yes.
the oxidation state comes over here, it's +3. So name goes as you have kept everything correct only except the oxidation state. Pentaamine carbonato, right? Cobalt, oxidation state 3, and chloride. Clear?
Yes, ma'am.
Very good. Here we go with the next now, anion complexes. So we'll finish today IUPAC nomenclature. Anion complexes. What are anion complexes? I would say the metal atom, right? Ligand and sphere holds the negative charge over it. So see, it can be holding either the negative charge or left hand side the metal. Like example, K4, FeCN6, right? So when they get ionized, what do they give? 4K plus FeCN whole 6 and that many negative ion. So this complex ion, what do you call as anion complex? Because it is holding negative ion, and when it is possible, either they will be holding negative, sign will be represented, or left hand side metal will be present. So this is how we identify if the complex entity outside left hand side, if atom is present, potassium, sodium, or any metal atom is present, then we can say that atom is called as, what do you call, that will be ionizing and giving out the entity as the negative one. So how do you name this compound? The first name goes to the metal atom. Okay, here for anionic complexes. The rule goes over here. Name of simple. So what do you call this? Potassium, call potassium. Simple cation outside the complex. And then same as usual. Name of the ligand So name of the ligand will be going as per the alphabetical order. Clear? Then after we have over here little change with the metal atom, central metal atom. That is basically Latin name chosen over here for the metal atom. Like if you have iron, you call it as a ferrum. Okay? Do not call as the iron while writing the name. So we will be calling it as by name, Latin name, all the central atom. Are you clear? So I will be giving the list to you, the most commonly asked the metal atom and their Latin name. In the Latin name, the suffix we need to add as the ATE, Latin name of metal ion with holding suffix. What is that? ATE. Clear?
Yes.
Okay. Then we come to the oxidation state as usual rule. Oxidation state. And here we do not get the right hand side any name. So that's all, because instead of that we are getting left hand side. So that's all. Let's see the example. Here we go with the rule, naming rule. Follow for the anionic complexes. So let's do the first one, K4FeCN6. So how do you name this? 4 or 5 does not matter to us. Just we write potassium. Numbers will not be represented for the outside complex name. Come to the hexa as usual. Hexacyanido. Correct? Oxidation state. What is the oxidation state? +2, right? Right, Hridaya?
Yes.
Okay. Now the central metal atom Latin name is ferrous. You know, right? The we are removing. And what are we adding? We will remove um from this and ATE we will add. So the name goes over here, ferret. Did you learn?
Yes.
This is the Latin name of the iron. Ferrum. So we have done little change in this. What is the change? We need to remove from here and then add ATE and then we can bring the ferrate. So potassium hexacyanide, ferrate, okay? And the oxidation state we have calculated to Roman numeral. That's all. Did you learn?
Yes, ma'am.
Okay, Hridaya. So here we go with the some metal with their Latin name. Okay, so I would be writing directly with the ATE suffix. That would be better, right?
Yes, ma'am.
Okay, so the metal name, okay, Latin, its Latin name with ATE suffix. Okay, so let us begin with the iron. So iron ke liye we use ferrate, cobalt, cobaltate, nickel, nickelate. Okay, then we have platinum, platinate, PLATNATE, platinate. Clear now spelling?
Yes, ma'am.
Okay. Palladium sometimes also they ask. So let us keep this also. Okay. So most common central metal I have written. Okay. In case if any other name comes, I would be giving you at that time. Clear? It is clear?
Yes, ma'am.
Okay. So sometimes they may not have compound left hand side. Okay. They may give with the anion. So it is easy, right? It is anionic complex and the rule goes as the anionic complex ke liye. The central metal. So we go directly because we do not have any left hand side molecule of the sphere. So tetrachlorido Directly we go. Oxidation state will be -2. So write in a bracket and sorry, nickel. I forgot to write the metal atom. Did you understand?
Yes.
Will you do by yourself some examples?
Yes.
So do this one first. NiCN whole 4, 2 miles. Do this one by yourself.
Is it tetracyanonickelate?
Very nice. Tetracyanidonickellate. Oxidation state
2.
2. So here we go with the potassium. +2 X 0. So the oxidation state is +2. Did you understand?
Yes.
Hriday, you try this one. Yeah, Hriday. See, mercury, right? Tetra. And what do you call this as? Thiocyanate, SCN, right? So here I'll tell you, since S is ligating, so we'll write S. And then we will write the cobaltate name. Oxidation state, mercury oxidation state will be +1. Hriday?
Yes.
And this is -1, SCN minus, so -4 +1 -4 will be -3, and the equation will be equal to plus 3. Right? Means X is equals to plus 3. So the oxidation state is plus 3. Okay, Hridaya, can I give some example? Other examples? Will you try?
Oh, yes, ma'am.
Do this. Hear me?
Yes, ma'am.
Yeah. Do this by yourself.
Pentacarbonyl
Penta,
iron,
carbon, pentacarbonyl
iron,
iron. Very good. Do not write any Latin name over here, because what is common name used over here? Iron. After that, oxidation status
0,
0, because carbonyl is neutral. Very good. Well done. Do next one by yourself. PT, Br, Cl. No, change it little, because that will be little lengthier to you. PT, Cl2, NH3 whole twice. This one you do. Left and right side we do not have. Even the sphere does not carry charge. Yes, Hridaya?
diamine, difluorido,
Diamine, very good, because alphabetical order we have gone. Diamine,
uh,
dichlorido. Very nice. Then
platinum,
platinum, very nice. Oxidation state there.
2,
Very good. So did you learn?
yes, ma'am.
Right? All the names. Now let me just introduce the one last, where we have the double complexes. Double complexes ke liye how we write the name. Double complexes. So here, suppose we have the Ag, okay, NH3 whole twice, one complex. AgCN whole twice, other complexes. Correct. So no worry, where we will be like writing separately for them. So diamine will go as per the rule. There is no new rule. Diamine, silver. Okay, oxidation state will be 0 here, right? But wait, just a wait. Okay, we consider, we'll write later the oxidation state. Then you write for this nido. Okay, and why did I say to wait? Because you can see over here we have amine, here we get the oxidation state as 2, correct? So silver cannot have 2 oxidation state. So what happens basically when we get the oxidation state of silver as a +2, it will be distributed equally. Understood? It will be distributed equally. So here we go with the silver, like carries the one negative charge, and this means extra having electron, and this goes over here one, right? The positive. So the positive ke liye we carry the positive over here, and we write here as the, but this is not visible to you. Are you understanding? This is not visible to you. This is understood that one silver, because silver oxidation state cannot go +2. So how it is getting distributed among these two, making it neutral. So one carry one positive, one carry one negative ion. Since it is anionic complex, so we will be writing the Latin name argentate. Did you learn? And the oxidation state -1, because here -2, here -1. So -1 plus 2 will be answer 1 plus 1. And here 0 and equation equal to +1. So oxidation state is +1. Did you learn the oxidation state? How to check? So
Yes.
there,
Yes,
yes.
ma'am.
So this is applicable for, so this is imagine, this is all rough work. You are not going to do at the main sheet. Are you clear? This is how we need to do. Okay, can we go with the one more example and then wind up? Just
Yes,
check
ma'am.
this one. PT NH3 whole 4 in a one bracket. Okay, and PT Cl4 in another bracket. Do this one. So you will see always the other will be the neutral, other will be the anion. So the anion will go for the sphere holding anion and other will be going cation. This is how they will make it neutral, and the number whatever this is carried, suppose two are there, so equally divided, 1 and 1. Okay? If 4 are there, then 2 and 2, like that divided. Now you do. Yes, Hridaya, tell the name.
Uh,
Tetraamine,
Tramine,
hmm, platinum,
platinum,
hmm, oxidation state will keep in bracket, then tetrachlorido, this will become platinate. Now oxidation state, when you calculate over here, it comes 4 plus 4. Now this is getting distributed among these two equally. This carries -2, this carries +2. So the here oxidation state Roman numeral 2. Now let us calculate -4 plus 4 -2 here, right? We get the -4, I meant to say. So this here we have -2. So minus when it goes here, plus becomes, so we can get the +2 as the oxidation state here as well. Did you understand, Hridaya?
yes, ma'am.
Okay. So I will send you homework and this notes today. So this is about the complexes, double complexes we have learned. We are done, completed our nomenclature topic. We are left with the three important rest topic in this chapter. Tomorrow this chapter will be over. Okay, Hridaya?
Yes,
So
ma'am.
but it is all depending how much practice you are doing. So this is most, as you can see, the 6 marks in your hand, fixed question from this chapter. Okay, so you have to prepare accordingly. So 6 marks if you wanted, you have to be ready with the oxidation number calculation. You have to ready with the definition of the homoleptic, heteroleptic, chelating, denticity, monodentate, bidentate, tridentate examples. Okay,
Yes,
all
ma'am.
these things. Yeah, so I'll be sending in with examples. So
Yes,
see you tomorrow, and please complete and send me the homework, which I'll send after your class. I will send. Okay, most probably in the evening.
yes, ma'am.
Okay, Rudya. See you tomorrow then. Bye bye.
Thank you, ma'am. Bye.